Okay, so in this lecture, I'm going to cover the basic theory relating to linear mixed models. So this is in many ways the crucial lecture in this course because everything that we have learned so far is now leading up to understanding this framework of linear mixed models. The linear mixed modeling framework is the current state of the art in data analysis. We don't do repeated measures ANOVA and even t-tests anymore. In our research, we generally always turn to the linear mixed model. So it's very important to understand the machinery behind it. And this lecture, as you can see, is going to be relatively long. So it's 90 slides, right? So I would like to request your patience as you work through this lecture. The material is very important. I mean, not that the other material was not important, but this material is kind of central to this course. And I want you to leave this course with a very solid understanding of how the linear mixed model works and how to do model selection and so on. Okay, so what do we know so far? We know how to do simple t-tests. We know how to fit simple linear models with continuous or categorical predictors. And we got a little glimpse of the connection between the t-test, the paired t-test, and the linear mixed model, right? Because I showed you that the estimate of the t-value from a paired t-test is the same as that from a varying intercepts linear mixed model several lectures ago. So that's the background to all this. We also know how contrast coding works in the linear modeling framework. All that knowledge can now be used automatically in the linear mixed modeling framework, right? So I'm going to go back to my favorite data set, which is subject and object relative clauses in English. I like this data set because it's simple. It's a clean experimental comparison between two conditions, and it basically illustrates everything that I want to teach you about model data analysis and model comparison and all that stuff. So everything that we learn with this simple encapsulated example can be scaled up to more difficult research problems. Okay? So that's why this data set is so important to me. It illustrates a lot of the important ideas. So we have subject and object relative clauses as before. I won't introduce the design again, but basically I've done +1, -1, some contrast coding as usual. I created a vector by hand that I'm going to use in my model, right? And I've extracted the critical data, the relative clause data in this file that I just loaded. And I've renamed the data object as dat, and then what I did was I created a new vector that log transforms the data, the observed to reading times. And I explained earlier why I want to do that. I want to meet the model assumptions better. And then the next thing that I do is I aggregate the data by subject so that the item level variability is collapsed now, because for each subject I have only one data point in each condition. I hope you remember this story. Okay. So I'm working with by subject data here. The reason I'm doing that right now is that I want to simplify the problem a little bit and only talk about by subject variability. Later on, we will look at the DAT data frame, which is unaggregated, and we will take the by item variability into account as well. And that will be the real data analysis that we do. Okay. Anyway, so working with... there's actually a mistake here. So I'm actually working with the unaggregated data here when I'm fitting the simple linear model. Okay, so don't be confused. I will keep pointing out when I'm working with the aggregated data and with the unaggregated data. So this linear model is already wrong. Okay, so the model itself is completely wrong. Why? It's wrong because this is repeated measures data. Every row in the data frame is not independent from every other row because we have repeated measurements from its subject. So this model is wrong, but it doesn't matter. All I want to show you here is that the fixed effects intercept and slope coefficients of the model on the log millisecond scale are shown here. Okay, so So I'm going to show you what happens to these intercepts and slope estimates when we fit a linear mixed model. Okay. Now, first of all, this simple linear model that I've just fit is over all the subjects data. So there are 42 subjects in this data set. So I have fit a single linear model over all the data, right? Now what we could have done is that we could have fit a separate linear model for each of the 42 subjects. That is completely reasonable, because for each subject, now if I have, I don't know how many items there are, but whatever the number is, let's say 16. So then I have 8 data points from each subject for subject relatives and 8 for object relatives. And so that basically gives me a way to talk about each subject's linear model fit, okay, in the subject object relative clause comparison. So what I've done in this figure is that I've shown you 4 random subjects. I've just chosen 4 subjects and shown you the linear model estimate, the output of the LM function for each of the subjects. Okay, so what you see here, what you should notice is that for subject 1, I have an almost flat line. That means the slope is practically 0. That means that the subject 1 doesn't show much of a difference between subject and object relatives. Now look at subject 28, this guy here, right? Here the slope is very steep. So what that means is that for that subject, the object relative clause, which is the thing that is coded as +1 on the x-axis, the object relative clause leads to longer reading times than the subject relative clause in subject 28. Okay. By the way, I just want to point out something interesting here, that in subject 28, the distribution of the 8 data points for subject relatives is very tightly clustered together, but in the case of the object relative, it's widely spread out, you know. And so this the extreme values that you're seeing here, these 2 extreme values, they are actually pushing the average object relative clause effect of subject 28 higher, and that's why the slope of this line is so big. Okay, so that's why we see such a strong effect in subject 28 due to those extreme values, right? So because if you think about it, this data point here is log 8 milliseconds. What is log 8 milliseconds on the millisecond scale? Let's take a look. Okay, so here's I'm just going to take the exponent of 8, right? That's almost 3 seconds. So this data point here is 2981 milliseconds, right? That is a pretty slow reading time for reading a verb like saw or something like that, right? Imagine spending 3 seconds staring at the verb saw while reading. 1, 2, 3. I mean, what kind of cognitive process is going on in your head? Probably you're checking your email or something, you know, while reading that thing, or maybe you're texting someone or something. I don't know. Maybe 3 seconds is too short for that, but you're certainly zoning out, you know. So that data point looks rather suspicious to me, and so this effect of this subject might be exaggerated. You know, the big difference you're seeing between the 2 conditions, the big slope, could be a result of a few extreme values. Similarly in subject 37, again we see very slow reading times. This is even larger than log 8 milliseconds, so it's more than 3 seconds, you know. And this is also pushing up the slope of subject 37 pretty high. Subject 38 is showing tightly clustered estimates, data points for subject and object relatives, and the slope is like practically 0 here. Okay. So you can see, what you see here with these 4 subjects data is that there is individual level variability in the slope of each subject, right? And if I showed you all the 42 subject slopes, you would see that there's quite a lot of variation. Okay, so we're going to follow this strategy of fitting a separate linear model for each subject, and then we're going to plot the intercepts and slopes on top of each other to see how much variation there is. Okay. So we're going to do all this on log reading times, right? Because I discussed that earlier. We want to satisfy model assumptions, and that's why I want to do that. So it turns out that there is a function in the LME4 package that allows you to do this kind of modeling, fitting a separate linear model for each subject. Of course, you could do this by hand. What you could do is you could write a for loop. Well, let me just do this. Okay, so this is a very stupid way to to fit a separate linear model for each subject. Okay, so what I would do is I would create a subject list. Okay, a list of subjects, which would basically be a sequence going from 1 to 42 by step size 1. So that this basically means that I'm going to, oh, this is actually a very complicated way of doing this. I'm very stupid. I should have just said 1 to 42 are the subject IDs. Okay, that's it. So now I've got the subject list, and now what I would do is I can save the number of subjects as the length of the subject list, right? Okay, so that's going to be 42, right? There's 42 subjects in this data set. And then what I would do is I'd just run a for loop going from 1 to, for I going from 1 to n, where n is 42. I'm going to run the following for loop. What I would do is I would take my so let's say I have my unaggregated data, the DAT data set. So I would just subset the data such that the subject ID double equal sign is the ith element in the subj list. Okay, so subj list is a vector containing 42 values. I just take the ith cell, so I is going from 1 to 42, right? I take the ith cell of subj list and choose that subject ID and subset that data for so I'll call this D for data right now. And then what I do is in this for loop, then I could fit a linear model to the log RT, right? It was log RT or something as a function of SO for my current data set D, and then I could save that as the model object M, and then I could extract the summary, you know. What would be the summary? I could say summary for model M and dollar coefficient. If I say summary M dollar coefficient and I extract, let's say, the first column and the first two rows, right? So this, what I wanted to write here, I'm sorry, it's not very neat here, is 1 to 2 comma 1, right? This gives me the intercept and slope estimates, and so I could extract that. And so of course I need some kind of store. I need to store these values somewhere, so I could store it in some matrix, call it M, which I would have to declare here, right? I would have to declare some matrix here. So I could, in this for loop, I could save all the intercepts and slopes for each subject by writing this for loop. This is a very clunky way of doing it. Now it turns out that where was I? Sorry. Yeah, I wanted to be back in these slides. So there's a very simple piece of syntax in LME4 that automates this process for you, right? So what this syntax does is called the LM list. So basically what this function does is that it fits an LM model for the grouping factor that you're interested in. The grouping factor we're interested in is subject, right? So in our data frame, did I print out the data frame? Let's take a look at what the data looks like, right? So I don't want to rush through this right now. So let's load the data. Here we go, right? So first I have to change to the correct directory. Okay, so let's go here. We got the data, we subset everything, get the aggregated by subjects data, and now I'm going to fit a separate linear model for each subject. And the way I'm going to do it is, let's go here, right? So I've got the LME4 function and I fit a separate linear model for each subject. So I just want to remind you here what that looks like, what the data frame that looks like, right? So what we are seeing in this data frame is that we have a column for subjects, column for items, We have a condition column which marks the subject and object relatives. We've got the raw RTs which we are not using. We created a new vector called log RT that contains the coding, the log transformed version of the data. Then we have the contrast coding +1 -1 for subject and object relatives. Okay, so basically what this function, the lmlist function, does is that it will fit a linear model log RT as a function of subject object relative clause for each subject. Notice that you could have done this for items as well. You could replace subject with item and you could have a separate linear model for items also, right? But right now we are only focusing on the subjects. Alright, so going back to the presentation here on the slides. So what I've done is, got distracted here. Right, so I've fit my lmlist function, and what this will give me, I've saved the results in this object. What this will give me is a matrix of intercepts and slopes. There'll be 42 different such intercepts and slopes because there are 42 subjects. I've fit a separate linear model for each of them. Okay, so I can extract the first subject's coefficients, the intercept and slope. You can see for subject 1. For subject 28, what you notice is that the subject has a different intercept. Okay, so this subject 28, is much slower on average compared to the subject 1. How do I know that these are average reading times? Why am I saying that the intercept is representing the average reading times? Well, the reason is that I have some coding. Some coding makes sure that the intercept represents the grand mean. Okay, so what I can see here already is that subject 28 is much slower than subject 1 on average. And we also see, if you look at the slopes for subject 1 versus subject 28, you see that subject 1's slope is practically 0.04. Compared to that, subject 28 slope is gigantic. On the log scale, 0.44 is dramatic, right? And so on. You can see subject 37 and so on. So you can extract the data for each of these subjects. Now what is easier to see, this is not very easy to get an impression of the 42 subjects. Like if you look at each of these sets of numbers, you could certainly do this mechanically, but it's a real pain to have to look at the numbers. You can look at this graphically. Okay, so that's what I've done here. I just extracted the intercepts and slopes for each subject and I just plotted them on top of each other. So here you're seeing the subject relative condition, here's the object relative condition, and what you're seeing, the red line that you're seeing, is the grand mean linear model that I had fit earlier over all the data, ignoring the fact that it's the wrong model. I just fit the linear model and I've drawn that line. But what you're seeing with the black lines is the amount of variation in the slopes and the intercepts of all the subjects. So some are slower, some are faster overall, so the intercepts are different, and some have steeper slopes and some have horizontal slopes. Okay, so what we are seeing here is between subject variability on the intercepts and the slope of the linear models. There is between subject variability here. Now, having fit these separate linear models for each subject, you could actually do a significance test to find out if there is an overall effect of relative clause type. And the way you would do this is that you can simply check whether the 42 slopes of the subjects, right? So I'm going to have, for subject 1, I'm going to have a slope beta 0, intercept, and a slope beta 0 and beta 1. These are my estimates for subject 1. So I'll give it an index 1 like this, right? For subject 2, I'll have another estimate of the intercept and another estimate of the slope. So I'll call this beta 1, 2, and so on. So I will have 42 slopes from these models. So I have a vector of 42 slope estimates, right, from the separate linear models that I fit for each subject. And so what I can do now is I simply extract that vector of slopes and check whether I can reject the null hypothesis that those numbers are different from 0. Okay, that's the standard one sample t-test. Alright, so that's exactly what I've done here. I extracted the second coefficient, the slopes, from the model, So these are coefficients. I've extracted the second one, and I just do a one sample t-test on that. So I've got degrees of freedom 41. Why? Because I have 42 subjects. So 42 minus 1 gives us the degrees of freedom of the t-test. So that is already an indication to me that I'm doing everything correctly, right? Always look at the degrees of freedom when you do a t-test and make sure that you have the right number there. And so what I see here is that I can reject the null hypothesis, right? The t and p value tell me that I can reject the null hypothesis that there is no overall effect of relative close type. Okay, so the test that I just did is basically the paired t-test, right? The one sample t-test is exactly the same thing as the paired t-test, and this paired t-test could have been done in a different way. Remember that I aggregated the data earlier. I have the by subject aggregated data. That means I averaged over the items, right? I could have just used this old methodology that I taught you many lectures ago on doing the paired t-test. Okay, I could simply have done that, and when I do that, I get exactly the same results, right? What I get is a t-value of 2.8102. That's exactly what I got when I did this separate linear modeling approach, right? So what this tells you is that fitting a linear model for every subject separately, extracting the slope and doing a t-test on the slopes is the same thing as doing a paired t-test on the aggregated data. It's exactly the same thing, right? It's a little bit mind-blowing if you think about it, right? That like any way you analyze this thing, you always end up with the same, same test in the end. Okay, but I want to blow your mind even further, because I can take the aggregated by subject data and fit a linear mixed model now. Of course, I have not explained what that is, but I'm going to now. But I'm going to use this Elmer function to again fit a linear mixed model for the entire data set, the aggregated data. And when I extract the t-value, the absolute t-value, lo and behold, is exactly the same as the paired t-test that I had just done, and it is exactly the same as the by subject linear model fit based analysis that I had done. Okay, so basically all these three approaches that I just showed you, they're exactly the same approach. They're mathematically identical. Okay, so now the big mystery is, what is this linear mixed model? So let's try to understand this a little bit better. Okay, the method that I had shown you of fitting separate linear models for each subject, this thing is called repeated measures regression, and there's a very famous paper by Lorch and Meyer, I think Lorch and Myers, 1990, that actually discusses this approach. So you can, I mean, it's just for historical interest. You're never going to use it, but it is a possible way to analyze this kind of data, right? It's not a wrong way. It's the correct way to analyze data. It's just that it ignores the by item variability because you aggregate over all the items. Okay. All right. So our ultimate goal actually in this course is to analyze unaggregated data. No averaging by items, but we're just going to take the whole data set and model all the sources of variability. Okay, so as I say here, what I've shown you, these methods that I'm showing you here, they're only of historical interest to us now. The real data analysis is yet to come. Okay, all right. So, oh, sorry, one more thing I wanted to say is that all these methods are of historical interest to us, but in the general population, in psychology and linguistics and psycholinguistics, people still use these outdated methods. So you will still see in top journals, you will see published papers with pairwise t-tests. Okay, hopefully they're doing the t-tests correctly. As I've shown you earlier, that's not trivial either, but people are still using these old style methods for doing data analysis, even though they don't need to, because we have linear mixed models now, right? So what I want to teach you in this course is how to get to the state-of-the-art methodology and not use these oversimplified methods. And the reason you shouldn't use these oversimplified methods is that they hide important sources of variability. This paired t-test that I'm doing is over the aggregated data, and this is hiding the by item variability. You're pretending that you don't have by item variability in the data, and that is an incorrect assumption. There's actually a lot of by item variability in many experiments. Okay, so you want to take that into account in your modeling. Okay, so where was I here? Yeah, so the linear mix model is basically doing something very similar to fitting a separate linear model for each subject. It's doing something very, very similar, but there is one crucial twist in all this, and that crucial twist is expressed in the syntax through this piece of code which says one vertical bar subject. That piece of code is the only extension beyond the linear model that you observe here. If you look at the syntax here, let me erase all this stuff so we can rewrite everything neatly. So okay, so let's get back to right. So if you just concentrate your mind on this piece of code here, this part of the code in the Elmer function, right, is just a simple linear modeling code, right, that we've seen before. Right. The only new thing here is this part here, where I've added one vertical bar subject. And the important thing to understand is, what is this piece of code doing? By the way, I made a mistake here which I will fix later on. I should have written SO here in order to stay consistent with my sum contrast coding, but right now I've ended up with treatment contrast coding because I forgot to use the correct predictor. Okay, it's not a big deal, because as you know, for treatment contrast and sum contrast, the slope, the hypothesis test associated with the slope is the same one anyway, so I'm still golden, you know. So that's why I ended up with the same t-test regardless of how I did the contrast coding. I hope all this is clear, right? Okay, so right now our goal is to try to understand in the Elmer function, what does it mean to have, I've got log RT as the dependent variable, SO as the predictor. What does it mean to have one vertical bar subject, right? What does this piece of code actually mean? Okay, so what this code is doing is that it is okay, so now I have done the correct sum contrast coding, right? So what this code is doing here is that it's adding it's adjusting the grand mean intercept, right? Remember that the intercept is going to be, this intercept is the grand mean. What this piece of code here, the one vertical bar subject, is doing is that it is specifying the deviation. It's ensuring that every subject has an adjustment around this grand mean. So the subjects that are slower, a subject that is slower than the grand mean, so this represents the grand mean, this number, right? If a subject is slower than the grand mean, then I have to add an adjustment to that subject's intercept to represent the fact that that subject is slower. If a subject is faster than the grand mean, then I have to add a negative adjustment to represent the fact that that subject is faster than the grand mean. Okay, so basically what we are doing now is that we are going to be defining a model where we have the grand mean intercept beta 0, we have the slope, but we are going to have an adjustment term for each subject that adjusts the intercept for that subject. Okay, so this part of the model you guys already understand. Okay, you understand this part of the model very well. We have the grand mean intercept, we have the relative clause deviation around the grand mean estimated here, and the statistical test is being done here, and so you can see what's going on here. What's new in the linear mix model is the following. We have, of course, the estimate of the standard deviation of sigma, so the residual variance, right? That is this number here. But in addition, we have one more source of variance. That source of variance is telling you how variable the subjects are about the grand mean intercept. Okay, so imagine that if you did an experiment with, let's say, 42 subjects like here, and all the subjects had exactly the same average reading time. This is never going to happen, but suppose it did. In that case, this standard deviation would be 0. right? So it's representing between subject variability in the average speed of all the subjects. Okay. All right. So notice another thing, that the intercepts and slopes that we have here, they're exactly the same numbers that we got in the simple linear model that we fit at the beginning of the lecture, where I ignored the fact that I had repeated measurements and I just fit a single linear model on the whole data set. I will have the same estimates, but what will differ now is the standard error of those estimates, right? And therefore the t-values will also differ. Okay, so that's an important thing to notice here. Now, as I mentioned, the interesting thing here is that I have an adjustment to the grand mean intercept. I have an adjustment by subject. I can actually view those adjustments by using this piece of code. There's a random effects function, ranf, which takes the fitted model, and you can extract the first 10 subjects intercept adjustments. Okay, so that's what this piece of code is doing, and you can see that some subjects have negative adjustments. So this is the subject 1, who is faster than average. Okay, and then you've got some subjects, for example, this guy here has a very large positive adjustment. This is on the log millisecond scale. 0.23 is quite large. So this subject is way slower. So this is subject 4, probably is way slower than the average speed of the subjects. Okay, so you can see the by subject variability in the grand mean, of each subject. You can also visualize the by subject variability, so the between subject variability and the average speed, by using this dot plot function from the lattice package. So if you run this function, what you will see is for all the 42 subjects, so these are all the 42 subjects, you are seeing the different intercept adjustments. Okay, that's what you're seeing here, and these are called random effects here because they're showing how the 42 subjects vary around the grand mean. Okay, the horizontal bars along each of the estimates of the subjects are 95% confidence intervals, so they're telling you how much uncertainty you have, roughly speaking, for each of the estimates of the 42 subjects. Okay, so the model that I just fit, this model called m0.elmer, right, is basically can be represented mathematically, right, in the following way. So suppose that I identify the each of the subjects. So I've got 42 subjects, right? I equal to 1 to 42. So I is going to index subjects, okay, and let j index the items. Okay, so I don't know how many, 16 items or something I have, right? So basically in the data frame dat, which is the unaggregated data, once I know the subject ID and the item ID, I'm going to get a unique row in the data frame. This is because the subject, so the experiment is designed in a classic Latin square design. So let me quickly explain that. This is very important to understand. If you've never seen a Latin square design before, it is important to understand what it is, because all our data generation and simulation processes that we will study now in the coming lectures depend on assuming a certain kind of underlying design. Okay, and this is a classic Latin square methodology, design methodology that is used in psychology and linguistics, and we generally always adhere to this design. Okay, so the idea is I have two conditions here, object and subject relatives. So what I'm going to do is I'm going to create two lists, which I'll call two groups, group 1 and group 2, and let's say I have 16 items. Okay, so I have 16 items. Each of those items has a subject relative sentence and an object relative sentence. So remember, the sentences were something like the man who saw the woman left versus the man who the woman saw left. So these are the same words, but the word order is changed so that they become subject and object relatives. So let me call the relative clause conditions A and B, right? So I have a condition A version and a condition B version. So what I do is I take item 1 and I distribute the two versions of item 1 into the two lists. Okay, So for item 2, I'm going to reverse the ordering of the object and subject relative. So the object relative comes first and the subject relative second. Then for the third item, I'm going to write AB. For the fourth item, I'm going to write BA, and so on. So I keep doing this for the 16 items, right? And what that does is now that I have what I have is two groups of items, and each group contains only one version of each item. So there are 16 items, and that means that in group 1, I will have 8 versions of subject relatives and 8 versions of object relatives. But each item will have only one instance in that group. And the same thing holds in group 2. Okay. So now what I'm going to do is every time a subject comes in to do the experiment, I'm going to randomly assign them to group 1 or group 2 by just tossing a coin, right? If it lands heads, they land in group 1, otherwise they land in group 2. Of course, you can do this in more sophisticated ways using a computer, and typically when we run an experiment, we already predetermine the randomized order of group assignment for each incoming subject. Okay, I can talk about that. Ask me about it in a meeting if you're not clear on how to do this. But in any case, the point is that now from each of my subjects will be either assigned to group 1 or group 2, and so each of my subjects is delivering one data point for each condition from each item. And that is why it is true when I say that if I know the subject ID and the item ID, I can uniquely identify a row in the data frame. And to prove to you that that's true, I've done that now. For subject 1 and item 1, I subsetted the data. So I have data from subject 1, item 1, and lo and behold, I get exactly one row from the data frame that represents that subject's exposure to that item. Okay, it happens to be an object relative, and their response was 320 milliseconds. So the interesting thing here is now I can use the subject and item IDs, so the I and J IDs that I'm talking about here, to write down the mathematical form of this linear mixed model. Okay, so what I'm going to do is that I'm going to say that each of my log reading times can be uniquely identified by subject and item ID, I and J, in the following way. The estimated reading time for a particular subject reading a particular item will be represented by the grand mean intercept beta 0, the grand mean slope beta 1, which represents the relative clause effect, and which condition I'm looking at can be identified by specifying the I and J IDs. Okay, so I just look up the first subject's first ID, and I know if I look at this term here, I know whether I'm looking at +1 or -1, so I can actually do this calculation and write either positive beta 1 or negative beta 1 depending on which condition it is. Okay, so my mathematical model now is, let me just erase all this and rewrite everything now. So right, so my mathematical model now is this equation 1, and this equation is stating now that I'm fitting a linear model with an intercept and a slope just like the linear model before. There's nothing new here. The only thing new here is that for each subject I have a new term which I'm calling u sub 0, which represents a numerical value that's an adjustment to the grand mean beta 0 intercept for that subject I. Okay, that's the only new thing in the linear mixed model right now. Now the next thing I need to tell you is that we assume, the linear mixed model assumes, that these by subject adjustments u sub 0, which is indexed by subject ID I, are assumed to come from a normal distribution with mean 0 and some standard deviation, which I'm going to call sigma u0. I want to distinguish this standard deviation from the standard deviation of the residual, which we standardly estimate in the linear model, right? So now I want to remind you of something I showed you a few seconds ago, right? So if you remember, when I was showing you this linear mixed model output, okay, right, when I show you this linear mixed model output, I showed you these two sources of variance here. This first one here is the estimate of sigma hat, and this standard deviation estimate that you're seeing here is the sigma hat u0 that I'm talking about right now. That's the between subject variability in the by subject intercepts. Okay, so that's the estimate of that variability. So where was I? Here, right? So this is an assumption of the linear mixed model that the intercept adjustments are assumed to be generated from a normal distribution with mean 0 and some standard deviation that determines how much variation there is. So this is a parameter that the Elmer function is going to estimate for you, the parameter being sigma u0, right? So it's the Elmer function's job is to estimate the variability between subjects in the intercepts. So the big difference between the linear model is that the linear model has one intercept for all subjects. The linear mixed model has a separate intercept for each subject. So you can write that separate intercept in this manner here, right? So we can also visualize these adjustments to the intercept for each subject by plotting them. So what I've done here is the red line is showing you the grand mean, the linear model that I fit over all the data. The incorrect model I had fit at the beginning of the lecture. And these vertical, these black lines that you're seeing around the red lines, these are the linear mixed model estimates for each of the subjects' relative clause effect. So notice that the slopes of each one of these black lines is exactly the same as the slope of the red line. That's because we are assuming, if you look here, we are assuming that all the subjects have the same relative clause effect. The slope is the same for everyone. What we are assuming is that each subject has a different intercept, okay? And that is why you're seeing the fluctuation around the red line. Some subjects are slow, so this subject out here is very slow, and this subject is very fast, right? So they have positive and negative adjustments to this intercept. So the mathematical statement again of this model is going to be that we have the grand mean intercept, grand mean slope indexed by relative clause type, and we have an adjustment term to the intercept which is assumed to come from a normal distribution with some mean and with a mean 0 and some standard deviation sigma u0, and then of course we have the usual assumption of the residuals epsilon being normally distributed, okay, with some standard deviation sigma. So the model's job is to estimate parameters as usual. And which parameters will the model have to estimate? It will have to estimate beta 0, beta 1, it will have to estimate the sigma parameter and the sigma u0 parameter. So there are 4 parameters that have to be estimated now, okay? Alright, so by the way, this model is called a varying intercepts model because the intercept is assumed to be varying by subjects, okay? Alright, now until now we've been assuming that all the subjects have the same slope, right? So just to show you this model here, in this model I have one slope for all the subjects, and graphically also you can see that all the subjects have exactly the same slope, right? So this assumption can be relaxed, right? And in fact, if you cast your mind back to the beginning of this lecture, I showed you that different subjects have different slopes. Subject 1 was almost flat. Subject what was it, 28 was had a very sharp slope. So it's not very reasonable to assume that these subjects have the same slope, right? So how can you represent that in the linear mixed model? What we are going to do is we're going to have an adjustment to the slope as well by subject, okay? That's all there is. It's nothing very dramatic. So this was what we had earlier. We had the intercept adjustment, and now what I've done is I've added a slope adjustment as well by subject. And the way I would write this in the linear mixed model syntax, Elmer syntax, would be that instead of writing 1 vertical bar subject, what I'm going to write is I'm going to change this to 1 plus SO double vertical bar subject, okay? So right now you just have to trust me when I say that you need this double vertical bar. I'm just about to explain what that double vertical bar is doing, okay? But nevertheless, once I've defined this syntax, I've used this syntax, now I have a varying slope for each subject as well, okay? And so the output that I will get from the linear mixed model will now add one more source of variance in the model. What will be that source of variance? It will be the between subject variability in the slope of the relative clause effect. And indeed you see that here. What you see is that this is the estimate of sigma, right? The residual. Here is the old estimate of sigma u0. This is the between subject variability of the intercept, right? And here's the new term. This term, which I'm going to call sigma u1, will represent the between subject variability in the relative clause effect across subjects, right? And I mean, if you look at these numbers, right, what do you notice? What you notice is that the sigma, the residual, has the largest value. So the noise in the system is the largest, causes the largest amount of variability. The next biggest source of variability is the subject's overall speed, right? The average speed of each subject is very variable. And finally, what you see is that the between subject variability in the relative clause effect is relatively small compared to the average speed differences between the subjects. Okay. Right. So this is what this kind of model where I have a separate intercept adjustment for subjects and separate slope adjustment for subjects. This is called varying intercepts and varying slopes model. Okay. And this is by subject right now. We are only focusing on the by subject variability here. Okay. So now I can actually plot this by subject variability from the linear mixed model. And when I plot this against the simple linear model that I had fit at the beginning, what you notice is that the subject's estimates for the intercept and slopes are going up. Some are high and some are low. So that's the adjustment to the intercept that you're seeing there. But you're also now noticing that you should notice that the slopes of these subjects are slightly different. So these subjects have a bigger slope, and these subjects have a smaller slope, right? It's not very easy to see on this log scale, but I'm sure you can tell that there's a slight variation in the magnitude, in the angle of the lines, and that's telling you what the slope is. So there's some between subject variability. That variability is being estimated here by this standard deviation here. Okay. So this is the varying intercepts and varying slopes model. So now one question you should ask yourself is, what is the difference between that model that I fit at the beginning of the course where I use the lm_list function to fit a separate linear model for each subject versus the model that I'm fitting now where I have varying intercepts and slopes for each subject? So the difference between these two can be shown graphically as shown here. And what you'll notice is that when we use the lm_list function to fit a separate linear model for each subject, the slopes varied wildly between one subject and the next, right? So you can see a lot more variation in the slopes in the lm_list approach that we had taken. But in the varying intercepts and varying slopes linear mixed model, what you notice is a much more smoother tightening of the slopes. They don't look so wildly varying across subjects, and there's a reason for that, which I'm going to explain. So first of all, I want to show you how to visualize from this model with the varying intercepts and slopes, how to visualize the intercept and slope adjustments. Okay, so what I'm showing you here, earlier I'd shown you the intercept adjustments by subjects. Now I'm showing you the slope adjustments by subjects as well. So what you can see from the plot on the right hand side, these slope adjustments, the amount of variability between subjects in the relative clause effect adjustment is smaller than in the case of the intercept, and that is exactly what was reflected in the output of the linear mixed model, right? As I showed you earlier, what I showed you was that this variance component is representing the variability between subjects in the slope, and it's much smaller than the variability between subjects in the intercept. And so you are seeing that graphically here, right? You're seeing much more variability here and much smaller variability here, right? So that's what the random effects standard deviation estimates are telling you numerically, and you can graphically visualize them too, right? Alright, so the formal statement of the model, just to repeat, is I have a simple linear model, right? And I've elaborated on that simple linear model by adding an adjustment to the intercepts by subject, and adding an adjustment to the slope by subjects as well. Notice that I had to write this in brackets, the slope adjustment, because I'm going to have the grand mean slope, and I'm going to have some adjustment u1 indexed by subject ID to the slope, but I need to know for every subject and every item, so every subject I and every item j, I need to know whether I'm looking at a subject relative, object relative. That means whether I'm going to code this as +1 or -1, right? That information has to be available here outside the brackets so that I can add up these numbers and then multiply it with +1 or -1. That's why I've got a bracketing there, okay? And so the important thing here to notice is that apart from the standard residual standard deviation, I've added two new sources of variability, and these are called variance components in statistics, right? They're sources of variance, right, in the model. It is traditional in statistics to talk about variance, but in our course we generally talk about the standard deviation, which is the square root of the variance. So I will sloppily call the standard deviations also variance components, okay, even though technically that's wrong, okay? So just because of historical convention, we call them variance components and not standard deviation components, and that's why I will keep using variance components even when I'm talking about standard deviations, okay? So now we have two new variance components in the model: the intercept adjustment, the between subject variability in the intercepts, and the between subject variability in the slopes. And I will follow the convention in this course of calling the intercept adjustments U0. So the intercept adjustments by subject will be called U0, and the slope adjustments by subject will be called U1, okay? So I will always try to use this convention. So one important thing that I showed you earlier was that the relative clause effect variability in the linear mixed model, so this is the Elmer model that I'm showing you here, this is the LM list model, right? The big difference you should notice graphically is that there is a lot less variability in the slopes in the linear mixed model compared to the LM list model. Why is that? The reason that's happening is due to a phenomenon called shrinkage, which I will now explain. So when we fit a separate linear model for each subject using the LM list function, right? So I'm using LM list to fit a separate linear model for each subject. For each subject, I have only 16 data points, 8 for one condition and 8 for the other condition, right? So what that will do is that it will give me very sparse data for estimating the relative clause effect for that subject. The linear mixed model, what it's going to do is that it's going to take advantage of the fact that I know all the 42 subjects data, and therefore I can compute the grand mean of those 42 subjects, and as a consequence, when I estimate the grand mean intercept for a particular subject, I'm going to drag that grand mean toward, I'm going to drag that subject's estimate towards the grand mean. That process is called shrinkage. You shrink the estimates of each of the subjects towards the grand mean. Why would you do that? Right? That's the question is interesting. Why would I even want to drag every subject's estimate based on their own data, the 16 data points from each subject? Why would I want to drag that estimate closer to the grand mean? Intuitively, this makes a lot of sense, because if I take all the subjects mean reading times, then I have a very good estimate based on a large sample size of the average speed of these subjects. Now I know that these subjects are going to vary around this average speed, but because I have very sparse data from each of these subjects, what will happen is that the estimates of each of the subjects based on their 16 data points will suffer from type M error, right? So they will tend to be exaggerated estimates. And so What shrinkage does is that it conservatively drags the estimate closer to the grand mean on the grounds that the grand mean is a more realistic estimate of that subject's average reading time. So any extreme values deviating from the grand mean will need to be conservatively brought closer to the grand mean. That's the basic intuition here, right? And so an important consequence of what I'm saying here is that if you happen to have less data from a particular subject, say you have half your data missing from a subject, this happens all the time, right? Especially in eye tracking data, you lose a lot of data points due to tracking error or something like that, right? If you have less data from a given subject, what the linear mixed model function does is that it shrinks the estimate of the subject even closer to the grand mean. And the reason it does that is that it believes the subject level estimates, right, even less than when you had all the data from that subject. So this is the big advantage of shrinkage, and I'm going to now show you exactly what happens. Okay, so if you look at just focus on the estimates from 3 of our subjects in this 42 subject data set, right? So subject 28's estimate, what you're seeing with the red line here is the linear model I fit over all the data incorrectly at the beginning of the course, right? And then what you're then seeing in the solid black line is the linear model I fit for subject 28 using that subject 16 data points. And the broken line that you're seeing is showing you the estimate from the linear mixed model. And what you notice is that if I just use the 16 data points from subject 28, I get an exaggerated estimate of that subject's slope of the relative clause effect. If I use the linear mixed model estimate, I get a conservative shift, the broken line, closer towards the red line. Okay, so that's shrinkage in action. Okay, you see the same thing in subjects 36 and 37. Right, the thin black line is an extreme estimate of the subject slope, and it's conservatively pushed towards the grand mean in the linear mixed model. So that's the broken line that you see. Okay, so that's shrinkage in action. So now I want to show you the dramatic effect of shrinkage if you have missing data. What I'm now going to do is I'm going to remove half the data from a particular subject's data set. So I have 16 data points. I'm going to delete half the data from the subject and pretend I don't have any data. So the way I'm going to do this, I'm using the R binom function to generate a sequence of zeros and ones, right? So I might get something like 1 1 0 0 0 1 or something like that. So that's what this rand vector contains. And then what I'm going to do is I'm going to look at subject 37, okay? And if I can look at the data available for subject 37. So here are the 16 data points that are available for this subject, and you can notice that there are some extreme values here. You see that? Some very long data points here, so, reading times here. So what I'm going to do is I'm going to copy that vector of raw reading times to a new vector which I'm calling deleted reading times. Okay, so I've done this, created a brand new vector which I've renamed as deleted reading times. And what I then did is that just for subject 37 in the vector called deleted reading times, right, just for subject 37, whenever the vector rand, remember this vector rand, whenever this vector has a value 1, I'm going to delete the data, right? So whenever the value is 1, I put an NA instead of the reading time. So I just remove the reading time, put an NA in there. Otherwise, I put the actual observed reading time of that subject. So what happens when I do this kind of thing is that I convert the data for subject 37 from those 16 data points that I had, these 16 data points I had, I've now got a data vector for subject 37 where I've got 1 2 3 4 5, I've got 5 missing data, or was it 6 maybe? I don't know, 4, 5, yeah, 1 2 3 4 5 6 missing data points. Okay, I've deleted some data here. And so now if you look at the original estimate that I got from the model where I'm fitting a separate model for each subject, and if I extract the intercepts and slopes for subject 37, that's what I've done here. I've extracted the intercept and slope for subject 37, right? You'll see that the intercept is 6.6 with the full data set, and the slope is 0.35, right? Now once I can do the same computation. I can fit a separate linear model for using the deleted data, right, over all the subjects, but what I'm interested in is the action with subject 37. So let me extract the intercept and slope for subject 37. Earlier the intercept was 6.6. Now the intercept is 6.8, much slower. Oh, sorry. It was earlier, it was 6.617, and now it's 6.68, right? So the difference between 6.61 and 6.68 doesn't seem very large, but actually it is quite large on the log scale. Let me show you. So the exponent of 6.1 is 445, and the exponent of 6.8 is almost double that amount on the millisecond scale. Okay, so that's quite an impressive slowdown. After deleting half the data, I've ended up with a much slower average reading time. Okay, and the slope also becomes much larger, 0.38. If you remember, the slope was 0.35 earlier, right? So what has happened is that by deleting half the data, I end up with more extreme estimates of the intercept and slope for that subject. That is type M error in action. Now, if I were fitting a separate linear model for each of these subjects, I would get an over-enthusiastic estimate for the slope effect, 0.38 instead of 0.35. That's a big difference if you're doing a t-test on the log scale. Okay, so to show you the dramatic effect of the linear mixed model, right, you have to now understand this figure here. So this figure is showing you, first of all, it's showing you with this orange line here, it's showing you the linear model that is fit over all the data, the incorrect model that I had fit at the beginning. Okay, now the linear mixed models with the original data for subject 37 and the deleted data for subject 37 are these two broken lines. And so what I want you to notice is that these two broken lines are sitting on top of each other, right? Those two lines are actually over here. This is a very impressive fact. The linear mixed model's estimate for subject 37 is completely unaffected by the fact that half the data for subject 37 is missing. The reason it's unaffected is due to shrinkage. Because in both cases, the full data set and with the half deleted data points, the estimates for the slope of subject 37 is being shrunk towards the grand mean. And so the linear mixed model is completely unaffected by the fact when deriving the estimates for subject 37, is unaffected by the fact that some of the data are missing from subject 37. Now, by comparison, look at what happens with the LM list functions when you have the original data, which is the solid black line, this one here, versus the deleted data. That's the thin black line that you're seeing. What you see is that there's a dramatic difference in the slope of between those two lines. And what that means is that just deleting 6 data points out of those that we have available for this subject, we managed to get a radically different slope for that subject. Well, radically different is an exaggeration, but certainly a bigger slope, 0.38 versus 0.35. In the case of the linear mixed model, there's virtually no difference, right? That's shrinkage in action. Okay, so the big advantage of the linear mixed model is that when you have missing data, the linear mixed model will still give you pretty conservative and accurate estimates of that subject's effect. Okay, so what missingness does to us, the bad thing about missingness is that it will lead to type M error, and what that will do is it will give you over enthusiastic estimates of a particular subject's effect, and therefore you can end up with significant effects that will not pan out if you try to replicate that experiment. This is why linear mixed models are such a big deal, because they are shrinking the estimates of the individual level effects to give you more conservative and more accurate estimates. Okay, all right, so now we're going to step up the action a little bit, and we're going to start thinking about the unaggregated data and scale up this model to its full glory. Now we're going to fit the full linear mixed model very soon. So one thing to notice in this data set, the unaggregated data, is that for each subject I've got one data point from each item. right? That's a function of the Latin square design I told you about. So this kind of setup is called a fully crossed by subjects and by items design. Okay, and this is the property of the Latin square setup. Whoa, I'm sorry, you guys can't even see what I'm doing here. I'm very sorry. I must let me go back a little bit. Okay, so I'm afraid that I may have missed a lot of this stuff, and you may not have actually seen what I'm doing. Right, so I'm sorry, I messed up my screen just now, and so I just want to make sure that I've already explained this clearly now. So what's happening here, if you look at this figure here, is that the linear mixed model is completely unaffected. The linear mixed model is completely unaffected by the fact that you have deleted or undeleted data, right? The lines, these broken lines, are sitting on top of each other, right? You can see that here. But the lmlist function estimates for subject 37 for the deleted versus original data have very different slopes. You can see that here as well. Okay. So that's what I was getting at. I'm not very sure now whether you saw that when I was doing this, right? And so just to repeat what I had just said, the big advantage of the linear mixed model is that when you have missing data, you're going to end up with overestimates for each of the subject's effects, and the linear mixed model is unaffected by that missingness because it will conservatively shrink the estimate of each subject towards the grand mean and therefore it will give you more accurate estimates of that subject's effects. Okay, so now coming back to this this fully crossed design, which I foolishly was not showing you on the screen but was just seeing on my own screen. So the situation I want to talk about next is the linear mixed model, where I have the full unaggregated data set, and that means I've got data from each subject and each item, and I'm not averaging anything now. And so a property of the Latin square design is that each subject is going to see one item once exactly, and that's what you're seeing from this xtabs function here, right? So this kind of setup where one subject sees exactly one item is called a fully crossed design, and it's a property of the Latin square setup. Okay, all right, so in order to take into account the fact that I have multiple items, I'm also going to have to now think about the fact that my intercept might differ by item as well. Right, so I might have to have an intercept adjustment by items as well, and similarly I may have to have a slope adjustment by items as well. What this means scientifically is that not only will subjects have different average processing speeds and different relative clause effects, the items may also have certain properties. There might be certain words that are being used that cause an overall slowdown in reading time or speed up in reading time, and there could be different situations being described in different items that lead to bigger relative clause effects or smaller relative clause effects. So there could be between subject and between item variability in the intercept and the slope. To express this variability between items for the intercept and slope, we're just going to add one more term, which is just like the 1 plus SO double vertical bar subject syntax. We're going to add that for the items. Okay, that's the only new innovation here, right? So now this is the fully crossed subject and item random effects setup. Okay, what this will do, the output that you will get from the linear mixed model, the fixed effects, this stuff is not going to change much, right? But what will change is that the number of variance components in the model has increased, right? So earlier we had the residual standard error, we had the intercept adjustment standard deviation, the slope adjustment by subject standard deviation. So this was called sigma u0. This one was called sigma u1, right? So I'm going to have to give new names for the item adjustment standard deviation to the intercept and to the slope, right? So I'm going to call this intercept adjustment to by the intercept adjustment by items, I'm going to call sigma W0, and the slope adjustment by items I'm going to call sigma W1. Okay, so basically what we have now, this is sigma here, right? So basically what we have now is 5 variance components in this model, and they're a consequence of adding these adjustments to the intercepts and slopes by items. Okay, so now you can again visualize the subject level intercept and slope adjustments as well as the item intercept and slope adjustments, right? What you should notice here is that I have 42 subjects here and I think just maybe 16 items here, right? So what you should notice is the variability, the uncertainty of these estimates is quite large, right, compared to the subject level estimates. And that's because the reason there's so much uncertainty in these estimates is that I have very few items. I have only 16 items, right? And each of these items comes with So I'm sorry, I just misspoke here. So what I mean is not that I have just 16 items. What I mean is that I have, so this, for example, this item's estimate of the mean and the uncertainty is coming from the 42 subjects, right, that saw this item in one particular condition or the other, right? So I have 42 data points coming in that are giving me an estimate of this item's variability, right? And now it just turns out that the subjects are very variable, and that's why my the estimate I have for this item is going to be quite broadly spread out, right? So that's why I'm seeing so much variability in the so much uncertainty in the estimate for each of the intercept adjustments for subjects, for items, sorry, in both the intercept adjustments and in the slope adjustments, right? Because subjects are very variable and their subjects data are going into this estimation here. Okay, so maybe this was not very clear, but I will come back to this in one of the exercises to make this much more transparent by giving you a practical problem to think about. Okay, so I'll get back to this. All right, so the linear mixed model that we have built up so far is the model with crossed subjects and items random effects, right? With the assumption that, so what is the formal statement of this model? Did I write it down? Not yet. Okay, so let me just write down the formal statement of this model, right? So what this model is actually doing formally is saying that for every subject I and every item j, I'm assuming that there is a grand mean intercept and there's an intercept adjustment by subjects and an intercept adjustment by items, right? And for the slopes, I've got a grand mean slope, and I have a slope adjustment by items and a slope adjustment by slope adjustment by subjects. This is by subjects and this is by items. Okay, and then I've got my SO coding for subject and item, and then I've got my epsilon for every subject and item, right? So that's the full model. But what's interesting here is that the variance components have to be written down. Okay, so I'm going to formally write down the variance components now. First of all, I have the epsilon, which is assumed to be normal with mean 0 and standard deviation sigma. Then I've got U0 and U1 and W0 and W1. These are my 4 sources of variation in the model, and these all have normal distributions associated with them, right? Right, and so I'm going to assume that all of these, so the model assumes that all of these adjustments have mean 0 and some standard deviation associated with them. So this is going to get very tedious now because I'm going to have to write all of these: sigma U1, sigma W0 and sigma W1. Okay, so this is the full formal specification of the cross subjects and items random effects model. Okay, but what is important to notice here is that I'm assuming for the moment that the intercept and slope adjustments of the subjects and of the items, right, they are completely independent of each other. So notice that here, here, and here, I'm defining two independent random variables for the intercept adjustment and the slope adjustment. They're two completely independent random variables. That is an assumption that I'm making here, and that independence assumption of the intercepts and slope adjustments is being expressed by this double vertical bar syntax here. That's what that double vertical bar syntax is saying, that you should assume that the intercept and slope adjustments are independent of each other. So now I'm going to change that assumption in the next model, and I'm going to have a single vertical bar instead of two vertical bars in the subject and item random effect specification. Okay, so let's see what's going on here now. All I've done is I've changed the double vertical bars to one vertical bar, and what this does, just to give you a little preview, what this is going to do is that it's going to ask the model to assume that there's a correlation between U0 and U1, the intercept adjustments and the slope adjustments, and it's going to assume that there's a correlation between W0 and W1, the intercept and slope adjustments by item. Okay, all right. So when you fit such a model where you assume such a correlation, what will happen is that you will get output that is just like the output that you saw earlier. Okay, so these are the 5 variance components that I already discussed, but in addition you will also get estimates of the correlation between U0 and U1 and W0 and W1. Those are the correlations that you're getting. Now here I've written that this correlation is degenerate. I will explain that in a moment. I hope I remember to do this, but I'll try. Okay. So, but the interesting thing to notice here is that these correlations are now being printed out by the model, because the model is now assuming that there is some correlation between the intercept and slope adjustments. Notice that the fixed effects are not changing at all. Nothing has changed here. Okay. The t values are going to be changing, but we'll discuss those things later, right? So now I want to quickly remind you, well, not remind you, but quickly tell you about what a bivariate distribution is like, how you define a bivariate distribution. So bivariate distributions are something that we encounter all the time. For example, our height and weight is correlated, right? So that's a bivariate situation. So if you take the heights of all the people in the University of Potsdam and the weights of all these people, and you look at the plot of the heights and weights, you will see a positive correlation, right, between them, I assume. Okay, so, but if you think of the bivariate situation where you have heights and weights, for example, you can talk about the relationship between these two variables by plotting them in 3 dimensions. So one variable is extending along this axis, the other variable is extending along this axis. What I've done here is I'm plotting a variable called U0 and U1. So what I'm trying to get you to visualize is a situation where you have different intercepts for each subject and different slopes for each subject, and there is a possibility that, so one possible outcome could be that the intercepts and slopes could be positively correlated, right? What that means is that if so each of these dots represent one subject's intercept and slope. So one possibility could be that the larger the intercept adjustment of a particular subject, the larger the slope adjustment of that subject. What that would mean scientifically is that the slower subjects tend to have larger relative clause effects. This actually makes a lot of sense theoretically, right? People who are slower at processing might actually take longer to complete the linguistic processing that's needed. So you could expect a positive correlation between the intercept and slope adjustments, right? So to express that positive correlation, you have to think about a bivariate distribution where you've got some distribution of the U0 scores and some distribution of the U1 scores, right? So what I'm showing you here right now is this smooth cone, which represents an uncorrelated situation where U0 and U1 are completely uncorrelated. So the picture that you would, if you looked at this cone from above, right, and not in 3 dimensions, what you would see is something like this. You would see you would see no distinct pattern, right? You wouldn't see something like this, like a positive correlation. You would see no distinct pattern, just a blob, a uniform blob, right, from above. Now, if there had been a positive correlation between these two variables, so if I was looking at this cone from above, right, I would see a tight clustering of the values along this ridge, right, along this ridge here, and so I would see this positive correlation if the two variables had been negatively correlated, right? So then if I looked at this cone from above, what I would see is something like this, right? I would see a ridge. If I'm looking at it from above, I would see a tight clustering of the data along this ridge. So that would be a negative correlation, right? So you can imagine a bivariate distribution either in 3 dimensions like these cones that I'm showing you, or from above you can see them in 2 dimensions. Okay. Now mathematically, when you have a bivariate distribution like U0 and U1, the way we write it down mathematically is that we say that the two variables U0 and U1 come from a bivariate distribution. This is how you write it. A bivariate normal distribution is what I'm assuming here, with some mean. In this case, both the means are 0 and some variance associated with it. The variance in a bivariate distribution is expressed in a very special way. It's not just a standard deviation, because there are 3 pieces of information that have to be conveyed in a bivariate distribution. One piece of information is the standard deviation of the first random variable. The second piece of information is the standard deviation of the second random variable, and the third piece of information is the correlation between the two, right? So that's why the way that we express the variance in a bivariate distribution is in terms of a so-called variance covariance matrix. And the variance covariance matrix will show on the diagonals. On the diagonals, it will have the two variances of the two random variables, and on the off diagonals it will have something called the covariance, which you have actually encountered in a previous lecture when I was presenting the matrix formulation of the linear model. So basically the covariance between U0 and U1 is going to be what? It's going to be the standard is defined to be the standard deviation of each of those random variables multiplied with the correlation between those two random variables. Okay, so the variance covariance matrix in the off diagonal gives you this covariance. So and you'll see the same covariance on both off diagonals. So this is called a symmetric matrix because of this symmetry around the diagonal that you have. Okay. Alright, so this variance covariance matrix actually determines the correlation and the standard deviations of the two random variables. And just to remind you of the output of the linear mixed model again, where is it? Here, right? So let me erase all this. The variance covariance matrix for subjects, for example, right, is going to now basically be shown here. This is giving you a summary of the variance covariance matrix for subjects, right? So basically the sigma for subjects is going to be the following variance covariance matrix. The standard deviation for the intercept is 0.31. I'm just going to use 2 digits, so let's say 0.32 squared. So you write the variance in the variance covariance matrix and not the standard deviation. The variance for the slope adjustment is going to be 0.11 squared, right? This number here, right? And the correlation is 0.58. So the correlation will go into the covariance, off diagonals here. So I'm going to write the covariance now. So the covariance is going to be 0.31, or is it 0.32? Sorry, 0.32 multiplied by 0.11. The two standard deviations. This is the definition of covariance, multiplied by 0.58, right? And the same number will turn up here, 0.3, because it's symmetric, right? 0.32 times 0.11 times 0.58, right? So the variance covariance matrix is expressed in this output in the linear mixed model, right? That's what the linear mixed model is doing. It's estimating erase all this. It's too noisy here. Yeah. So what this linear mixed model is doing is that it's estimating these parameters for you: the sigma u0 parameter, the sigma u1 parameter, and the rho u parameter, right? For the subjects. For the items, it's also estimating something similar. So sigma w0, sigma w1, and the correlation rho w, right? So that's what you see here when you look at the output. And what you're seeing is the correlation for subjects is 0.58 and the correlation for items is 1. Now what I'm saying here is that this number 1 is degenerate. What that means is that this correlation makes the variance covariance matrix, this matrix here, it makes the matrix degenerate. What this means is that when the correlation in this off diagonal part is +1 or -1, what will happen is that this variance covariance matrix sigma cannot be inverted anymore. It's not invertible. This is just a property of symmetric matrices, and so if this matrix is not invertible, then you can't do any of those operations that you need to estimate the parameters, right? So you remember that matrix inversion was a big deal for us when we were estimating the beta parameters and so on. So a non-invertible matrix is called a degenerate matrix, and it is technically a problem when you're actually doing the the mathematical calculations. Now one thing to notice is that the linear mixed model function just quietly prints out the +1, and it doesn't give you any warning that something bad has happened, right? So this message was written by me. This is not written by Elmer, right? So when you look at this output, everything looks just fine. I don't know why the developers of the Elmer software don't write a warning for the beginning user that a +1 -1 correlation leads to a degenerate variance covariance matrix, right? But it doesn't. Okay, so you just have to know that the +1 and -1 is telling you that the matrix is degenerate. So what should you do in that situation? What you should do is don't even try to estimate that parameter. So you should back off whenever you get a +1 or -1. You should back off to a double vertical bar syntax, and then you don't get an estimate for the correlation parameter. Okay. Alright, so this was a bit of a digression on bivariate distributions, and the reason I brought it up was that you need to know what lies behind the random effect structure that is being printed out by Elmer, right? I had to explain the bivariate distribution for you to understand what the output actually means. Okay, so now right now we are looking at a very simple case where we have just intercept and slope, because we have only one predictor. But soon we'll be looking at very complex designs with a 2x2x2 setup or something like that. You will have more than one slope. Okay, so you can actually end up with a variance covariance matrix that if there are two slopes, for example, then your variance covariance matrix will be a 3x3 matrix. Okay, why? Because there will be one variance component for one slope, one variance component for the second slope, and then there will be a third variance component for the third slope. So that gives you a diagonal with three elements. And if this is a symmetric matrix, there's going to be a 3x3 matrix that you're looking at now, right? So these variance covariance matrices in a multivariate distribution with, let's say, 3 random variables would give you a larger variance covariance matrix. That means more parameters have to be estimated now, right? So one question that you should think about now is a little exercise for you, is that suppose I have 8 random variables. Okay, so let's say you have a situation where you have a 2x2x2 design. This can happen in a 2x2x2 design, right? So what will happen now is that you will have your intercept, you will have your slope 1 all the way to slope 7, right? There'll be 7 comparisons, let's say. So if you do all these comparisons now, you're going to have adjustments to all the intercepts. So you will have 8 random variables, right? So how large will your variance covariance matrix be? It will be an 8 by 8 matrix. But the question I have for you is, how many correlation parameters will be in this matrix? Think about it, okay? Maybe you can tell me when we have a meeting on Zoom. Alright, so now the one thing I want to show you is that you can actually generate simulated correlated data just to get a good graphical intuition on how all of this works. Okay, so what I've done here is I created a variance covariance matrix which is like 1.6.61, right? So the variances of the two components are 1, and this is the correlation, right? 0.6 is the correlation between them. So I'm using the MVR norm function to generate 100 data points. The means of the two random variables is 0, and this is the variance covariance matrix. Okay, so I can produce that data which I've summarized here, and I can also graphically plot it, and you can see that there's a positive correlation over here, right? I could generate data with a negative correlation by changing these numbers to minus 0.6. Okay. Alright, so that's an exercise for you. You can try generating different kinds of data, including data with 0 correlation, right? If you change this to 0, if you change all these numbers to 0 here, right, then your matrix looks like this, right? Then you will notice that the data that you generate will look like this. It'll just look like a undifferentiated blob, right? That's what non-correlated data will look like. Okay, anyway, so coming back to our full linear mixed model with the variance covariance matrices defined in the random effects structure. So this part I explained to you, and then I also explained that by items you're not able to estimate the correlation parameters, so one should not even try. But nevertheless, this is now what we are learning from this model, right? So I'm going to ignore this degenerate correlation. But what I'm learning from the by subject intercept and slope adjustments correlation is that there is a positive correlation between the U0 and U1. That means the slower the average speed of the subject, the larger the relative clause adjustment for that subject. Okay, not for that subject, but the slower the speed of processing. Yeah, that's a better way to say this. What's happened here? It's frozen. Yeah, the slower the speed of processing, the larger the relative clause adjustment. That's what this correlation is telling me here, right? This could be theoretically interesting, you know, for us if we are trying to understand individual differences, for example. You might have theory about this, right? This is something I actually study. I'm very interested in the individual level effects when I'm looking at reading time data, for example. So this is not just of theoretical interest, it's actually of great practical interest if you're studying individual level effects. Okay. Alright, so the full mathematical statement of the linear mixed model with varying intercepts and slopes and with a correlation between the intercepts and slopes by subject and by item is now written down on this slide. Okay, so this is actually, I think all the components are familiar to you now. Here's my fixed effects intercept, here's the slope. Okay, this is the intercept adjustment by subjects, the slope adjustment by subjects, the intercept adjustment by items, and the slope adjustment by items. This is my plus minus 1 coded predictor epsilons, right? And the subject adjustments to the intercept and slopes are assumed to be correlated. They're coming from bivariate distribution, which implies a variance covariance matrix, which is specified here. And the items are also coming from a bivariate distribution, which implies a covariance matrix, which is specified here. Right? So how many parameters are there in this model now? So let's count them. Okay, I've got the intercept, the slope, 1, 2, right? And then I've got 3 parameters here and 3 parameters here. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 parameters in this model. This model has to estimate 9 parameters. Okay. Again, I can visualize the random effects, and this is the positive correlation that the 0.58 correlation that we saw earlier. What was the number? Sorry. Yeah, 0.58 correlation. What this is showing is that as these numbers increase, there's a small increase in this in the magnitude of the effect as well, right? So another way to plot this figure would have been to take each one of these 42 intercept values and the slope values corresponding to that intercept value and plot them like this. This could have been done. Maybe next time, the next time I prepare these slides, I can draw them like that, right? So it might be easier to see. In the case of the items, remember that the correlation we got from the model was +1, which I said is degenerate. You can see the degeneracy here, right? Because what's happening is that there seems to be a perfect correlation. What the model is showing you here for the intercepts and slope adjustments is literally a perfect correlation. It's a straight line here, right? And first of all, that is highly implausible, that there should be a perfect correlation between intercepts and slopes. And secondly, what's really happening here is that the model is, the underlying machinery, for estimating these parameters is actually failing to get an estimate, and it just lands at this extreme value and stays with it. And these dots that are being generated, they are being generated as a consequence of the failure to estimate that correlation, right? So once the correlation is set at +1, then these predicted values are produced by the linear mixed model, and they do not reflect in any way the reality of the item level intercept slope correlations. What's happening here is that we simply don't have enough data to estimate the correlations. Okay, if we had many more items, then we would be in a better position to get an estimate of this correlation, right? We have many more subjects, and that's why we were able to get a non-degenerate estimate of this correlation, right? Because we had a lot more subjects, but we can't really do that with 16 items, right? Okay, so I think that I will stop this lecture at this first part and then continue with the second part, because I still have another 40 slides to get through with this lecture.